Bad synonyms can wreck relevance. Search logs show the words users actually substitute. And DuckDB plus SentenceTransformers helps mine synonym candidates directly in Python. This is the setup you'll be able to run after this, which loads search logs and mines click-validated synonym candidates for safer query expansion. I'm Professor Pine, teaching search and IR with simple Python. People type many versions of the same intent. A user searches one way, then tweaks words until they click. Those tweaks are gold. They show which alternate words actually helped people find results. The goal here is simple. Turn those real rewrites into safe synonym candidates. Done carefully, that cuts failed queries and avoids adding broad synonyms that break precision. We'll pair a lightweight analytics engine with a semantic encoder. DuckDB gives you fast SQL-style queries on local files and can do session windowing without a ton of pipeline work. SentenceTransformers turns queries into vectors so we can judge meaning, not just token overlap. Together we look for rewrites that both happened in sessions and are close in meaning. Imagine a tiny log with 4 events. Someone tries a query, reformulates it, and then clicks. If lots of users make that same swap and clicks follow, that swap is promising. Semantic similarity weeds out accidental rewrites that only look related on the surface. The strength is that this uses real behavior. The weakness is that rare but correct synonyms need more data to show up. We'll build a small local pipeline. It loads a tiny event table into DuckDB, finds reformulations that led to clicks, embeds unique queries with SentenceTransformers, scores candidate pairs by combining support and semantic similarity, and then simulates applying a synonym to measure click gain. Everything stays concrete, so you can inspect the results. Now we'll load a tiny example into DuckDB. This snippet loads a tiny, readable set of search events into DuckDB and confirms the table's basic size. It first creates an in-memory DuckDB connection using the connect function. A create table statement defines events with user ID, query, timestamp, click document, a click flag, and session ID. The values block inserts 4 simple rows that include a reformulation and 2 successful clicks. The con.sql call runs an aggregate that returns the total number of events and unique queries. If you expanded this values list, both counts would grow accordingly. The printed counts confirm the data loaded and provide a quick sanity check before deeper mining. Next, we'll detect reformulations and measure which changes improved clicks. This code uses DuckDB window functions to detect query reformulations and measure their success. The SQL builds a subquery that partitions by session ID and orders by time, then uses lag to grab the previous query as prevq. It filters to transitions where prevq exists and differs from the current query, capturing reformulations users made. The outer query aggregates counts and averages the clicked flag to estimate a per-pair success rate. Finally, it orders by count and returns the top reformulation. A larger log would surface higher support pairs more reliably. The printed pair and success rate identify a concrete reformulation that users found helpful. Now, we'll embed the unique queries and inspect nearest neighbors. This example embeds distinct queries with SentenceTransformers to estimate semantic closeness. It reads unique queries from DuckDB using the con.sql call, then initializes the sentence transformer model, all-MiniLM L6v2. The encode function returns normalized embeddings, so their dot product equals cosine similarity. A simple nested loop scans the upper triangle of the similarity matrix to find the strongest off-diagonal match. The best tuple stores the two queries and their similarity score. Using a larger model may improve semantic nuance at the cost of compute time. Normalizing embeddings stabilizes comparisons, which makes similarity scores easier to interpret. The printed pair and similarity reveal which queries the encoder considers nearest in meaning. Next, we'll score candidate pairs by combining observed user behavior with semantic closeness. This snippet scores synonym candidates by intersecting real reformulations from DuckDB with semantic similarity from SentenceTransformers. It first builds a dict vec from queries to their embeddings computed earlier. The DuckDB query returns only reformulation pairs that ended in a click, filtering to observed successful corrections. For each pair, it computes cosine similarity via a dot product and multiplies by a log-scaled count, boosting candidates with more support. Increasing the log weight favors popular pairs, but may overfit. Reducing it emphasizes pure semantic closeness. The printed pair and score highlight a candidate that is both semantically close and proven by successful behavior. Finally, we'll apply the top safe synonym to a seed query and measure click gain. This code applies the mined synonym to a seed query and reports the click gain using DuckDB. It selects a seed Q0 and derives alt from the best safe pair found earlier. The first con SQL call counts clicks where the original query alone appears. The second counts clicks when expanding to a small OR set that includes the alternate wording. Subtracting gives a simple uplift metric that indicates whether the expansion recovered additional successful interactions. If alt were none or unrelated, gain would be 0. The printed clicks and gain quantify how the synonym improves retrieval outcomes without risky broadening. In production, you'd run the same steps as a batch job. Process larger logs nightly, persist candidate scores, and gate promotions with human review. The rule stays the same. Behavior finds candidates, semantics filters noise, and a small simulated uplift gives a sanity check before you ship. Recap. This is a behavior plus semantic pipeline that mines synonyms from real search sessions. Use it when you have even a small stream of query click logs and need safe query expansion. Caveat: low-frequency pairs need more data or manual review before you trust them. Next step, scale the same pipeline by indexing embeddings in an approximate nearest neighbor index and tuning the log weight to balance popularity versus pure semantic match. If practical, hands-on IR helps your search quality. Subscribe and watch the IR videos.